We're going to begin our exploration of the different types of chemical reactions by looking at what I would maybe call the simplest type, the synthesis and decomposition reactions. And one of the things that we're really going to try and do throughout our study of chemical reactions is gain an understanding of how the reactants that are present influence the products that are formed. This is just an overview of the 5 different types of chemical reactions that we will be looking at, and as I said today, we are going to focus on these 2 types. Our learning goals for not only today but throughout all of our study of the different types of chemical reactions will really be the same. We want to see how we can identify the type of reaction based on the information that's given. We want to be able to explain all of the different types of reactions in terms of some of the characteristics that define them. And finally, we want to use what we've learned about the characteristics and the features of some of the different subtypes to be able to predict the products. And we want to do that in situations where perhaps we know the reaction type, maybe we're told that information, but in other cases we will just be given the reactants and we have to make a call as to the type of products that are formed based only on those reactants. In order to help you organize your information for all of the different types of chemical reactions, I have included some placemats, so some placemat graphic organizers, which will help you take all of the information related to these learning goals and put it in a form that hopefully will be useful to you. So in simplest terms, a synthesis reaction is when you have 2 things coming together to form one. And you know what? It can be more than 2 things, but typically we have 2 reactants coming together to form one product. And so you get 2 things that are smaller coming together to form something that is larger or bigger. And quite often, the energy change associated with these types of reactions is that we see energy being released. And here we have more a pictorial representation of a synthesis reaction, and so see just 2 simpler things coming together to form one larger thing. And these examples show that same sort of message, where in the first case we have one element reacting with another element to form a compound, and the same thing in the second case. But don't forget that you can have an element reacting with a smaller compound to join together to form a larger compound. And we will see some examples of this later. Throughout our study of different types of reactions, we are going to make a connection to a dance analogy as just another way to help you remember and differentiate between the types. And so in the case of a synthesis reaction, we can think of it as 2 people coming together at a start of a slow song, and they are going to dance during the slow song. And so we have partner A and partner B coming together to form the happy couple AB. And again, another simple but I think effective representation of what a synthesis reaction is. So on your placemat graphic organizer, this is where you'll want to note the different types of subtypes for synthesis reactions. So in this first case here, note that we've got an element reacting with an element to form a compound, whereas in the second case, with the metal oxide and the water reacting to form the metal hydroxide, we've got magnesium oxide, which is a compound reacting with another compound to form one product. The key in both cases is that we have only one product being formed and we have multiple reactants. And the exact same thing happens down here with the nonmetal. So when a nonmetal reacts with oxygen, as is the case here, we get a non-metallic oxide being formed, and it turns out that these non-metallic oxides are acidic, whereas I didn't mention before, but the metallic oxides are basic, and we'll explore that idea more in class. But back to here, so when CO2 reacts with water, so one compound plus another, they come together to form a larger compound. And so here again is another case where we have two elements coming together to form a compound. One thing that I want to point out, when we use the word salt, we're actually referring to ionic compounds, and we've talked about this earlier in the course. But salt just doesn't mean table salt, sodium chloride. It's just a coincidence that that's the example used here. But salt is any ionic compound. And here we can also have nonmetals that come together to form a compound. A couple other reactions that maybe fall into some categories up above, but you may come across these as we work through, and so I just wanted to point them out specifically. So decomposition reactions we're going to see are actually basically the opposite or the reverse of a synthesis reaction. We have one reactant in this case leading to two or more products, and so anytime you see a single reactant, you know that the only type of reaction that it could be, based on the 5 that we're looking at, would be a decomposition reaction. And so something larger is splitting into something smaller. Quite often this requires energy, and this energy can come in the form of heat or electricity or UV light. And I've just included the symbols for these two. So heat is often indicated by a triangle over top of the arrow in the chemical equation, whereas the HV or H mu is sometimes shown to represent UV light. And so here we see more in diagram form. We've got our AB turning into individual elements or smaller compounds, A and B. And so one thing is becoming two, and if we make a connection back to our dance analogy, this is like the end of that slow song we were talking about, where the couple has now split up into individual partners. Taking a look at some of the examples here, again we've got a compound, water, splitting into an element, and here we've got a compound splitting into individual elements. And so one of the things to look for with decomposition reactions is your one reactant absolutely has to be a compound of some type, because elements can't split into anything simpler. And right here in this example, this triangle over the arrow, this is the symbol I was talking about that implies that heat is being used for the reaction to occur. And again, a simple diagram just showing the decomposition reaction. Again, on your graphic organizer now, looking at the different subtypes of decomposition reactions. Again, hopefully you see, or you can make some connections to the fact that these are the reverse of synthesis reactions. And so the first type, the carbonates, when they break down, they're going to produce carbon dioxide. And I think that's, or one of the products they will produce is carbon dioxide. And hopefully that helps you with remembering that. The other thing that's produced is the metallic oxide. If we have a hydroxide, so a metallic hydroxide in water, they're going to decompose into water and the metal oxide. And the metallic chlorates are going to follow the same sort of pattern in that they're going to produce the KCl plus the oxygen. And I think the big thing to look for in all three of these cases is that each one of these compounds is decomposing to produce a binary compound. And what I mean by that is a compound made of two elements, and then plus some other compound that varies depending on the type of initial compound or reactant that you have. So just like the metallic hydroxide decomposed to form water, so metallic hydroxides we know are basic compounds. Well, here this acid is also going to decompose to produce water, and then whatever else is left, in this case, so you have the non-metal oxide, it's sulfur trioxide, is the other product. Also some oxides, so for instance this metal oxide, which would be mercury 2 oxide, they themselves can also can decompose when heated. And both in this case and then in the final two examples that are shown here you just have those binary compounds that I mentioned before, so compounds that are made of two elements, and so the only thing that really can be produced when those things break down are the elements themselves. And so in this case here, looking at water, we've got hydrogen and oxygen being produced. Really important to note that even though we don't see O2 over here, in order for when oxygen occurs in its elemental form, it always occurs as O2. And there are those 7 compounds that we will talk about maybe a bit more in class, but that occur as diatomics. And they are hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. And so you really want to watch for the presence of those in these reactions, because you're never going to write this simply as O or this simply as Cl, because when they occur as elements, those 7 diatomics always occur as O2 or Cl2, etc., etc. And I know we talked about that a bit in the nomenclature unit, but it's an important thing to remember when writing chemical equations. So during this last little bit here, we just want to develop some strategies that we can use to predict products. And so I've told you that we have either synthesis or decomposition reactions, and you may or may not have that information all the time, but here we're going to keep it sort of narrow and focused. And so for instance, in the first case, we've got H2, which is an element, and Cl2, which is an element. So we've got 2 reactants, and so automatically that tells us then in this case that it has to be a synthesis reaction. And so those 2 elements are going to come together to form a single product, and that product will be HCl. And I'm not too worried right now about the states or about the balancing. I just really want you to focus on being able to predict the proper products. In the second case here with the zinc hydroxide, there's a couple of clues that we have a decomposition reaction. First of all, we only have a single reactant. And second of all, we've got this triangle up above, which indicates that heat is being used. And heat is often used as a way to induce decomposition or cause decomposition. And so our 2 products then become the metal oxide, which is the zinc oxide, and we also have the water. Because remember, anytime that hydroxides break down or decompose, one of the products that will be produced is water, and then the other is the metal oxide. And note that I wrote ZNO because the charge on the zinc is zinc 2+, and on oxygen is 2-. So those charges cancel out and they occur in that 1-to-1 ratio that we see. So again here I know that this third reaction will be a decomposition reaction, and since I have a carbonate, I know that one of the products that will be produced is carbon dioxide, and the other product is the sodium oxide. And conveniently enough now we have this reaction is balanced actually in this 1-to-1 ratio. We have the 2 sodiums, we've got the 1, 2, 3 oxygens, and we've got the 1 carbon. And then finally, taking a look at our last reaction here, we've got 2 reactants, so we know that it's going to be a synthesis reaction, and so my 1 product will be the AlBr3, and again I know that because aluminum forms an ion with a charge of Al3+, and Br is Br1-. And so when I cross those over, I get the AlBr3. Now, really important to note, some people will want to write AlBr2 because they're just going to take this and combine them. Remember, when you have 2 things coming together forming an ionic compound, as we have here with a metal and a non-metal, you need to take a look at the ions and the charges on those ions and write the proper formula using those charges. So that concludes our lesson on synthesis and decomposition reactions. Hopefully you were able to complete the placemat organizer I gave you complete all of the different categories in that placemat organizer for each of the different types of reactions. And don't forget to take a look at trying to find some applications of synthesis reactions and decomposition reactions in our world.